Hi everybody, welcome back. This is chapter 5, lesson 5, and we're going to talk today about Dalton's law of partial pressures. And I have an animation to explain that to you. So here we go. Did you get it? That's what it is. All right, have a great night. No, just kidding, really, but this does do a good job at explaining it. So let me pause it and explain for you for just a minute. Oh boy, I don't know how. All right, so how does this explain Dalton's law of partial pressures? Well, as you can tell from these cylinders, there's a red gas, and its pressure is 0.76. And there's a blue gas, and its pressure is 0.40. And then in the third cylinder, we mix the blue gas and the red gas together. And guess what their pressure is? It is the sum of their individual pressures. So if you add together 0.76 and 0.40, you get 1.16. So Dalton's law of partial pressure states that the total pressure of a mixture of gases, like this one, is the sum of the individual pressures. So this P3 is really equaling P1 plus P2's pressure. Okay? Let it run a little bit more and you can see another example of this. Okay, here it is again. P1 is 0.48 by itself, P2 is 0.40. We put them together. The total pressure is the sum of the individual pressures. So the total pressure would be 0.88. And we would say then the partial pressure of P1 is 0.48. The partial pressure of P2 is 0.40. That's all it is, okay? So partial pressure is just the pressure of an individual gas within a mixture of gases. Let's get some of that down in our notes, shall we? All right, so here we have in words exactly what we just talked about. And look they're even like blue and red and then the total, right? Just kind of like that video was trying to show you. In this example, the blue gas exerts a pressure of, say, 2 weights, and the red gas exerts a pressure of 5 weights. And so if we mix them together, the total pressure would be the sum of the individual pressures. P blue plus P red, 2 plus 5 would give us 7. And so the total pressure is the sum of the individual pressures in a container. We could actually calculate the partial pressure, right? That's how they will word it. Calculate the partial pressure of each gas by using Pivner, right? Where this is the pressure of gas 1 and the volume of your container and the moles of gas 1. And the temperature, okay? And, you know, we did this in our lab today where the total pressure was the atmosphere, right? Was the pressure of the atmosphere. And that really equaled the pressure of the water plus the pressure of the butane, right? So the total pressure that was being exerted was actually the sum of the individual gas pressures of water vapor and the pressure of butane, okay? You could also, if they just wanted total pressure of a mixture of gases, you could just use total moles here instead of using individual moles. All right, let's look at a sample problem. Mixtures of helium and oxygen are used in scuba tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 degrees and 1 atmosphere. All right, I gotta draw my helium. 46 liters of helium at 298 Kelvin. Remember, Leah, always convert the temperature of a gas to Kelvin. And a pressure of 1 atmosphere. Was mixed with oxygen, right? Or maybe we're not mixing them yet. 12 liters at 298 Kelvin and 1 atmosphere with pressure. So we have that much gas, and we're going to pump them into one tank, right, with a volume of 5 liters. Calculate the partial pressure of each gas in this tank. So they want the pressure of O2 in this tank and the pressure of helium in this tank, and then they want the total pressure in this tank. Okay. At 25 degrees. So we are maintaining a constant temperature of 298 Kelvin. That's important. So what we really have to do is quite a variety of problems here. We have to, I'm going to move this. We have to calculate first the pressure of helium when we put in the big tank. That will give us the partial pressure of helium in the big tank. And really what's changing is obviously going to be the pressure and the volume, because we're going from 46 liters of helium down to 5 liters. Temperature is constant, and so are moles and R. So we can simply do a Boyle's law equation, right? P1 V1 equals P2 V2 in order to solve this problem, because the temperature is not changing, the moles aren't changing, and the R's are not changing. So originally our pressure of helium was 1 and our volume was 46 liters. What will the new pressure be when the volume is 5 liters? That's what we're going to solve for, and that will give us the partial pressure of helium inside the tank. So 46, right, divided by 5 gives us our partial pressure of helium in the big tank to be 9.2 atmospheres. We'll do the same thing for the oxygen. We'll get the pressure of oxygen in the big tank. And again, same deal. The volume and pressure are changing, but nobody else is. So we'll do a P1 V1 equals P2 V2 to get our pressure of oxygen in the big tank. Our original pressure was 1. Our original volume is 12. What will the new pressure be when we smush it into a 5-liter container? So 12 divided by 5. Our new pressure is going to be 2.4 atmospheres. So I have already answered 2 of the questions that they have asked me. The pressure of oxygen, right? The partial pressure due to oxygen is 2.4 atmospheres. That's my final answer for that. The partial pressure of helium is 9.2 atmospheres. And since the gas molecules move and behave independently of each other, they don't attract or repel, the total pressure is the sum, like we just saw, of the individual pressures. So the total pressure is 2.4 plus 9.2, which is going to be 11.6 ATM. Okay, that brings us to mole fraction, which we're already aware of, mole fraction here. Mole fraction is the individual moles over the total moles, but a new twist to it is that it's the individual pressure. So we already know that mole fraction is the moles of component A over the total moles, but what you need to also know is that it's equivalent to the pressure of component A over the total pressure. So this here is a new relationship for us, okay? The partial pressure of oxygen was observed to be 156 torr in air. So the pressure due to oxygen is 156 torr when the total atmospheric pressure is 743 torr. Calculate the mole fraction, okay? Well, now we know that mole fraction is equal to the pressure of component A over the total pressure. So we can take 156 and divide it by 743. And that will give us the pressure of component A. So 156 divided by 743, which is 0.210. All right, I will save example number 3 and example number 4 for Monday. What I would like you to do, tomorrow in class you're going to be working on some practice questions and a practice test. And over the weekend, I would like you to do homework number 4 for Monday. So if you could take a look at homework number 4, that'd be fantastic. Have a great night, everybody. We'll see you in class on Monday.